Okay, these are the numbers for specific heat here. Cropped. But you can see iron. Iron is 0.45. If you look at these are metals here, a lot of metals. The metals are typically pretty low. What has the highest specific heat here? What has the lowest specific heat? Look at this. The lowest specific heat is the lowest is going to be the smallest number. What is the smallest number? Lead. Lead. Lead is 0.13. What is the highest? Magnesium. Well, actually, the highest is water, 4.18. And so what this means is the specific heat is how much heat is required to raise the temperature. So it doesn't take much heat to raise the temperature of lead. You know, just a little bit of heat and the temperature of lead starts going up. But if you add a little bit of heat to water, temperature really doesn't go up. Because its specific heat is so high, it requires a lot of heat to raise the temperature of water. And so the units for specific heat are this. The units of amount are grams. The units of specific heat are going to be joules per gram degree C. And so this is the amount of joules that are required to raise the temperature of 1 gram by a degree C. And so for lead, it takes 0.13 joules of energy or heat to raise the temperature of 1 gram of lead by 1 degree C. Whereas for water, liquid water, it takes 4.18 joules of heat to raise it by 1 degree C, 1 gram by 1 degree C. And so it takes a lot more heat. And so things with a high specific heat take a lot of heat, a lot of energy to warm up. Things with low specific heat don't take as much energy to warm up. See if that fits better. I don't know what happened to this. It's weird. Delta H of the phase transition. Well, we have different phase transitions. We have melting. Melting is also called fusion. So this is the heat that's required to melt a gram. So what has the lowest? Heat of fusion, which is the heat required to melt a gram. The lowest is going to be this one here, 11. 11 joules of heat required to melt a gram. And that would be mercury. So when we melt mercury, we need to know what is its melting point, the temperature at which it melts. Mercury melts at 39 degrees C. That seems off, but anyway, that's the melting. The highest heat of fusion would be what on this list? NaCl. In order to melt NaCl, it would require 519 joules to melt a gram. And its melting point would be at 801. So we have to heat it all the way up to 801, and then as you start adding that energy, it'll start to melt. Water is pretty high too, 333. And so heat of fusion is the amount of energy required to melt. Heat of vaporization is the amount of energy that's required to boil it. And so when we look at it, what has the lowest? Looks like the lowest is 0.3 mercury. Lowest. This is 0.3 kilojoules per gram. This is joules. So heat of vaporization costs more energy. Is to melt it, you're just partially breaking the IMFs. But to vaporize it, you have to completely break those IMFs, like we were talking about yesterday. And so here, mercury, what has the highest heat of vaporization? Water. Water has the highest here. The sodium chloride would be higher, but water has the highest on this chart, 2.26. Oh, that's right. Al, aluminum. Aluminum has very high. Aluminum is much higher, actually, 10.9 to boil aluminum. So that requires quite a bit more energy. Aluminum boils at 660 degrees C, or 2519. It actually boils at 2519, extremely high. It melts at 660. And so we need these temperatures in addition, because that tells us what temperature it melts and what temperature it boils. Now the reverse process of boiling is condensation. And so for condensation, we have to remove heat. And so for boiling, it's endothermic, so these are all positive. For condensation, we just put a negative sign there. And so if we're boiling aluminum, it's going to take us 10.9 kilojoules per gram. If we're condensing aluminum gas to liquid aluminum, it's minus 10.9. If we melt ice, it's plus 333. If we freeze water, we have to remove that. That's minus 333 joules per gram. So this is what we call a heating and cooling curve. I don't know why this is cropped like this. It's weird. Okay, if we start off with a solid, let's say the solid is below its melting point. This is the melting point for the solid here. If the solid's below the melting point, then if we add heat, this is adding heat as we go right. As we add heat, the solid warms up. And so this is like cold ice. Let's say you had ice at minus 10 degrees C. If you have ice at minus 10, does ice melt at minus 10 degrees C? What temperature does ice melt? 0 degrees C. So if you had ice at minus 10, what we have to do is we have to warm it all the way up to 0 degrees C before it starts to melt. It won't melt below 0 degrees C. And so what we'll do is we're first going to heat up the object, ice. And then once we hit the melting point here, all the heat goes into melting it. The heat does not go into increasing the temperature. The heat just goes into melting. That is breaking the hydrogen bonding interactions. And then once we've melted all of it, then we have liquid water. And so if we add heat to liquid water, the temperature increases. How hot can we get liquid water to? Can we heat liquid water to 150 degrees C? Is that possible? It's impossible, because once you hit 100 degrees C, what's going to happen to the water? It's going to start to boil. And so here we're going to heat the liquid water until it hits the boiling point. This is going to be 100 degrees C. Once we hit the boiling point, then the temperature doesn't change. You know, does the boiling point keep increasing or decreasing, or does it stay the same when you're boiling water? It stays the same. So that pot of boiling water is just going to stay the same temperature, because all that heat you're adding goes into breaking the hydrogen bonds completely, and we're vaporizing it. And so we get boiling here, and once we've boiled all the water, then we're left with steam. And the steam is going to warm up. And so here, this is it. Object warms. We use the equation Q equals mc delta T. And then there's a phase transition, melting. So we use the equation Q is equal to the amount times delta H. And then once we have liquid water, that's an object, liquid water warms. We use Q equals mc delta T. And then once we hit the boiling point, then there's a phase change. So we use Q is equal to amount times delta H. And then finally, Q is equal to mc delta T. That's what they have here for the calculations. And we're going to do some calculations. We want to figure out how much energy is involved in these processes. So we'll look at some of their calculations, and then we'll look at some of the book calculations. All right, what happened to this? How much energy is needed to vaporize 188 grams of a liquid if its heat of vaporization is 1.13 joules per gram? So what we're doing is we're vaporizing, and that means there's a phase change. So the equation we use is Q is equal to amount M times delta H. We're going to use delta H of vaporization because we're vaporizing it or boiling it. And so it's the amount, 188 grams, times delta H of vaporization, 1.13 kilojoules per gram. The grams cancel, and we're left with 212 kilojoules. And so this is only a phase transition here. We're going to boil 188 grams. How much energy does that take? The temperature is going to be at the boiling point. How much energy is required to melt? Okay, so we're going to melt 25 grams of ice. Well, what temperature does ice melt at? 0 degrees C. Since it's melting, we use this equation. Q is equal to the amount times delta H. The amount is 25.0 grams. Delta H, well, this is melting, so it's called fusion. Delta H of fusion is 333 joules per gram. The grams cancel, and that leaves us with 8.33 kilojoules, or 8.33 times 10 to the third joules. And so that's how much energy is required to melt that ice at 0 degrees C. How much energy is required to change the temperature of 25.0 grams of water from 10 degrees C to 50 degrees C? Here, it's staying as liquid water. There's no phase change. We're not going from liquid to solid or liquid to gas. It's just staying liquid water. So what we're doing is we're warming up an object. We're warming up an object from 10 degrees C to 50 degrees C. And so the equation we're going to use is Q is equal to MC delta T. Delta T is T final minus T initial. So M is the amount, 25.0 grams. C is the specific heat of water. So we look it up on the table. The specific heat of water is 4.18 joules per gram degree C. So 25, 4.18 joules per gram degree C. And then delta T is T final minus T initial. T final is 50 degrees C minus T initial is 10 degrees C. And so the grams cancel, the degrees C cancel, and that leaves us with joules. And it's going to cost us 4.18 kilojoules worth of energy to warm 25 grams of water from 10 degrees C to 50 degrees C. Calculate the total heat transfer when 19.6 grams of ice, initially at minus 12 degrees C, is heated to steam at 115 degrees C. And so can ice be ice at 115 degrees C? No. What's going to happen? If we have ice at minus 12 degrees C, when we warm it up, what's going to happen? Can we warm it up, ice, to any temperature we want? No, because once we start warming it up, it's going to stop at 0 degrees C. And so the ice is going to warm up. This is A. Ice warms up until we hit 0 degrees C. That's object warming. Object warming is Q is equal to, what's the equation? Q is equal to MC delta T. So ice warms up to 0 degrees C. Q is equal to MC delta T. And so the first part of this is this. The ice cannot warm up all the way to 115 degrees C. And so what we're going to have is ice warms from minus 10 degrees C to 0 degrees C. That's the maximum temperature we can have for ice, because then it'll start to melt. Now we need we need this. We need Q is equal to mc delta T. Okay, what is the amount of ice we have? The amount of ice we have is 19.6 grams. What is the specific heat of ice? So the specific heat of ice, we have to look it up, or we have to have it given to us. So we'll look it up here. The specific heat of solid ice is 2.06. What are the units here? The units are joules per gram degree C. They're way up there. And so this is going to be times 2.06 joules per gram degree C. Okay, then times delta T. Delta T is T final, which is 0 degrees C, minus T initial, which is minus 10 degrees C, which is going to be plus 10 degrees C. So the grams cancel, the degree C cancels, and that leaves us with joules. And so let's see how many joules we get. It's 19.6 times 2.06 times 10. 403.76. Now, we can't do this in one step, and so I'm going to call this Q for step 1. Step 1 is we have to warm up the ice. Okay, once we warm up the ice to 0 degrees C, if we continue to add heat, what's going to happen? What's going to happen is the ice is going to start to melt. So we went from minus 10 to 0. The heat was used to warm up the ice, 10 degrees. Now the heat is going to be used to melt the ice. Well, if we're melting ice, what equation do we use? Yeah. Okay, so in step 2, we have that the ice melts. And so I'm going to call this Q2 for step 2. How much heat is going to be brought? It's going to be M times delta H. Now melting is called, what's another name for melting? Fusion. So it's going to be delta H of fusion. And so what is the amount of ice we have? We have 19.6 grams of ice. And what is the delta H of fusion for ice? So we have to find that in the table. And so looking at the table here, I see the heat of fusion is 333 joules per gram at 0 degrees C. 333. So this is 333 joules per gram. And so the grams cancel. That leaves me with joules. And so this is going to be 19.6 times 333. This comes out to 6,526.8 joules. That's step. Two. That's a lot of heat to melt. So let's put in the numbers that we have so far. The amount of heat, let's say we're going from 0, minus 10 degrees C to 0 degrees C here. The amount of heat that's required for step 1, we just calculated, 403.76 joules. The amount of heat for step 2 is we're melting all this ice. So the temperature stays constant, we're going to melt all the ice. So if we melt half the ice, we're here. If we melt all the ice, we end up all the way over here. And the amount of heat that that requires is 6,526.8. 6,526.8 joules. That's a lot more heat there. Okay, so we did step 1, step 2, now we're going to do step 3. Once we melt all the ice, then we have liquid water. And so step 3 is just all the heat is going to go into warming up the water. So step 2 was melt the ice. Ice melt. We're going to melt all the ice. Step 3 is the water. Now we have water at 0 degrees C. So step 3, water warms. And the water is going to warm from 0 degrees C all the way to, what's the maximum temperature I could have water at? 100 degrees C, at which point it's going to start to boil. And so if I'm warming water, it's warming an object, what equation do I use? Yeah, and so this is going to be step 3. Q is equal to mc delta T. And so the amount is going to be 19.6 grams. What is the specific heat of water? A lot of people know the specific heat of water. It's 4.18 joules per gram degree C. Okay, but you can look it up in a book. Delta T would be T final, which is 100 degrees C, minus T initial, which is 0 degrees C. It's T final minus T initial. All right, so I have this, and then I'm going to go ahead and calculate it for step 3. $19.6 times 4.18 times 100. 8,192.8. 8,192.8 joules. Actually, this is water. You know, the reason is water has a very high, what? That's a lot of energy. It takes a lot of energy to warm up the water because water has a very high specific heat or heat capacity. And so this is not drawn to scale. This line should be the longest, but I'm not going to change it. This is 8,192.8 joules. And so that's even more than it cost us to melt it, which was 6,526. So once we warm up the water to 100 degrees C, if we continue adding heat, the heat is not going to make the water hotter. You know what the heat's going to do? It's going to boil it. And so step 4, the water boils. And so what equation do we use? The water boils at 100 degrees C. Ice melts at 0 degrees C. What equation do we use for this? Q is equal to amount times delta H of vaporization. Vaporization we use for boiling. If we reverse it, then we change the sign and use condensation. So Q is equal to amount times delta H of vaporization. Well, the amount is 19.6 grams. And so what is delta H of vaporization? Delta H of vaporization for water here is 2.26, but it's kilojoules. So delta H of vaporization is 2.26 kilojoules per gram. And so the grams cancel and leaves us with kilojoules. So what does it come out to? 19.6 times 2.26 equals 44. So I'm going to convert this to joules. I'm going to have 44,296 joules. joules. So boiling the water took the most energy of all. When we boil that water, it's going to take 44,296 joules worth of energy. And then we're going to warm it to, we're going up to 115 degrees C, to recall. Is that right? Yeah, 115 degrees C. And so once we boiled all the water, then that heat is going to go into warming up the steam. And so this would be step 5. And Q4. Step 5 is steam warms. The steam is going to warm from 100 degrees C to 115 degrees C. So it's an object warming. Steam would be the object. And so we're going to use Q is equal to mc delta T. The amount is the same, 19.6 grams. Now, the specific heat of steam, we have to look that up. The specific heat of steam is 2.00 joules per gram degree C. So 2.00 joules per gram degree C times our delta T. We're only warming it up to 115 degrees C. So 115 degrees C is the final temperature. The initial temperature was 100 degrees C. And so we're only warming it up by 15 degrees. And so this is going to be 19.6 times 2 times 15. It's 588 joules. So the final step here is going to cost us 588 joules here.